Welcome to this video on volumes of revolution, which is part of the Year 2 core Pure. It extends what we did in Year 1. So to start with, we're just going to recap what we did in Year 1 and actually extend it to some functions that you wouldn't have been able to integrate at that point. So a quick recap: if we take a function and we think of its graph rotated around the x-axis to form a solid volume, then the volume of that shape will be given by volume is equal to pi times y squared, and then we integrate the whole thing between values of x. So we often take the pi outside the integral, so we get the formula pi times the integral of y squared dx from a to b, where a and b are values of x. So if you remember that rotating around the x-axis, we're going to have dx here, and the y squared really comes from the formula for a circle, pi times the radius squared for the area of that circle. So we're thinking of volume given by little discs. I hope you can ignore the sound of the fireworks behind me. If we're rotating around the y-axis, then we're effectively swapping the x and the y around. It's the value of x that gives us the radius and the dy delta thin strips of y that give us the thickness of each disk. So we get this formula pi times the integral of x squared dy. And here the limits are for y, so we've got them written also as a and b here, but here the values of a and b need to be values of y. So got to be a little bit careful about that. So let's go ahead and look at an example. The region R is bound by the curve with the equation y equals 2 sine x, x-axis, and the lines x equals pi over 2 and x equals 3 pi over 2. So that's giving us our limits. Find the volume of the solid formed when this region is rotated through 2 pi radians, so that's a full rotation. Again, just watch out for where they ask you to find the value volume of something which is not rotated all the way around around the x-axis. So we're going to say it's about x, so volume is equal to pi times the integral of y squared dx, and then your limits are x equals pi over 2 and x equals 3 pi over 2. I would strongly recommend that you write out this formula each time. It's often possible, if you make a mistake later on, that you get a B or sometimes an M mark in an exam for doing that. So let's work out what y squared is. Well, we've got y equals 2 sine x, so y squared is equal to 4 sine squared x. So the volume is equal to pi times the integral of 4 sine squared x dx, pi over 2 to 3 pi over 2. How do we integrate sine squared x? Well, you should be familiar with this by now. You might like to just pause the video and work through this yourself first, and then just check that you've got this right. If this was part of the A-level upper sixth single maths integration. So what we do is we use the trig identity cos 2x is equal to 1 minus 2 sine squared x. So 2 sine squared x is equal to 1 minus cos 2x. So 4 sine squared x is going to be 2 minus 2 cos 2x. So this is equal to integral of 2 minus 2 cos 2x dx from pi over 2 to 3 pi over 2. And if we integrate that, we're going to get 2x minus sine of 2x. And when we differentiate sine of 2x, we get 2 cos of 2x. So that goes from pi over 2. I've missed out the pi here. I'm a bit inclined to do that. It's very easily done. 3 pi over 2. We're going to substitute in. So we're going to get pi times. Substitute 3 pi over 2 in here. And we're going to get 3 pi minus sine of 3 pi minus, this is going to be pi minus sine of pi, and sine of 3 pi is 0. And sine of pi is 0, so this is just 3 pi minus pi, so this whole bracket here is 2 pi, so this is equal to 2 pi squared. Now, one thing that is worth just looking at is a way of checking your answer, numerical answer on the calculator. So we'll just do that. I'm just going to switch to sharing my whole screen, and then I can go to the calculator. So you should be seeing that now. So what we can do now is we can put in the integral. So we can put in, we want pi times the integral, so shift pi times the integral of, we wanted 4 times sine squared x. Now, sine squared x, we're going to have to put in sine of x, close that bracket, and then square it. And then we're going to have to go and put in our bottom limit, which was pi over 2. So shift pi, and then down and put in 2. Then we're going to go along there, and we're going to put in 3, shift pi, and then 2. And now if we press equals, we've got another thing to check. We need, this is in degrees mode, so let's just go shift setup and 2, make sure we're in radians mode, and press equals again. So we get this value 19.739. We don't get an exact answer. You can check that exact answer matches what you got by working out the value of 2 pi squared. So let's just do that. 2 times shift pi squared is equal to 19.739. So you can see that we have actually got the same value there. Okay, so let's go on to the second example we've got, which is on the next page. Here's example 2. We've got this shaded region. Here's our curve. Lines y equals 5 and y equals 1. Calculate the volume formed when it's rotated around the y-axis by 2 pi radians. So let's do this. So we're going to say volume is equal to pi times the integral of x squared dy. This time we want the limits y equals 1. Let's just put it in there. Y equals 1, y equals 5. So we need to work out what x squared is. So y is equal to 1 over x squared minus 3. So y plus 3 is 1 over x squared. So x squared is equal to 1 over y plus 3. So if we put that into our formula here, we're going to say this is the integral of 1 over y plus 3 dy from 1 to 5, pi times that. There we go. Let's just move that up a little bit. So now we're going to integrate, well, again, this is a function that you couldn't integrate in your first year, but you can now. We're going to get pi times, integrate that, we get ln of y plus 3. We don't need to worry about modulus signs because both our values here are going to give positive values to take the log of 1, 5. So I think it's acceptable to leave out the modulus signs. So this is pi times, if we put 5 in here, we've got ln 8 minus ln 4, which is ln of 8 over 4, pi times ln 8 over 4, which is pi ln 2. Right, we're going to finish there for this start on the volumes of revolution. What we'll come back to in the next video is we'll look at volumes of revolution with parametric curves, and then we'll also look at some modeling with volumes of revolution. Thank you for watching. I hope that was useful.